Afternoon, everyone. My name is Michał Burdukiewicz, and I have a privilege and pleasure to introduce 4 fine guests of us who will discuss during this panel common statistical misconceptions. We are all claiming to be data scientists. We are analyzing data every day, and at least I can say from on my side, I'm doing it mostly wrong. And when I'm investigating my past mistakes, I feel really ashamed that I was publishing such research and doing such things. So let's correct our ways. And the best way to do so is to listen to someone who is actually proficient in statistics. We have great guests here: Olga Vitek from Northeastern University, Jaroslaw Harezlak from University of Illinois, Małgorzata Bogdan from University of Wroclaw, and of course our keynote from a second before, Harrell from University of Vanderbilt in a glorious Nashville, Tennessee. So I don't want to interrupt you more. The questions are I suppose are open. So let's start with the very big thing: p-value. Do we need them? Why we are using them? Thank you.
Who wants to start that? That was a loaded question. This is highly political. Olga, what do you think?
Well, yeah, indeed, right? So maybe as a start, let me just give you a little bit of background on myself and where I come from. So I'm a statistician by training, working in computational biology and specifically in mass spectrometry and proteomics. So we are collaborating with those experts who want biomarkers, and very few of them, if possible, right? And also at the same time, I am a faculty in the College of Computer Science. So I am teaching statistics to computer scientists. And I was also, until a few months ago, a director of the data science program at Northeastern. So it is a little bit spanning from computational biology to statistics to computer science. And the p-values, why they're popular? Oh boy, because they're easy. Right? Because it's easy to calculate, and because, you know what, my colleagues read papers, these other papers have p-values in them, so we need to do the same, right? So I think a lot of that is really cultural, right? And it is very clear that there are many flaws associated with p-values. So in my research in particular, so what happens is that we have to, so I'm working with proteomics, right? So we need to make some conclusions for the proteins that we quantify, and we have thousands and tens of thousands of proteins in our experiment. And so we effectively run models one protein at a time. So we will end up with 10,000 models that we have to fit, and we will end up with 10,000 p-values potentially for that. And I think the biggest message that I give to my collaborators is that a p-value is a random variable, right? So it's function of the data, which are random, and therefore p-values themselves are random. And so what we do a lot, just like Frank was talking about bootstrap and permutation, we do simulation-based approaches to show, okay, if we have that many replicates, you know, and this big fold change between conditions, let's just simulate a bunch of proteins with the same variance and the same sample size and see how often, what's the distribution of these p-values, right? And how often it's actually small, how often it's large, and what does it mean? And I think to us, it's kind of a intermediate solution, because it is important to show to our colleagues results in the language that they expect to see. And not because we surrender, but because we also understand the circumstances. For example, our colleagues, oftentimes they're PhD students, you know, they have bosses and bosses of bosses, and they need to kind of, we need to communicate these results, but showing, okay, these p-values, they're not fixed numbers, they're random variables. And this is what you can expect. And based on the distribution of p-values, you can say, okay, let us follow up on a certain number of proteins for which the distribution is consistently in a certain direction. So we're kind of in between a little bit, just based on our circumstances. But I am the first one to agree that this is really not necessarily the best way to proceed.
Małgorzata, would you introduce yourself and say something about p-values?
So you meant me or Dr. Bogdan?
Małgorzata.
Małgorzata, okay. So I am Małgorzata Bogdan. I work at the University of Wroclaw, and I work usually on feature selection, on model selection stuff, and in general on high dimensional data analysis. Okay, so let me maybe say a few words of what I think about p-values, okay? So p-values have some meaning, okay? So they kind of describe, I consider them as a kind of a measurement. It's a measurement which gives you some information about the signal to noise ratio in your data. So if your model is correct, okay, if your model describes reality, if your signal to noise ratio is weak, then the p-value will be relatively large, and you have an information that the signal is simply not strong enough compared to the inherent variability which you have in your data. So I think in this way, large p-value is an indication, but what you observe is not significant, taking into account the variability in your data. On the other hand, we have this problem with small p-values, okay? Because getting a small p-value is very easy. You just use a large sample size. Okay, so taking into account that most of our models are just approximation to reality, and very often your beta is never zero, but is some inherent variability in biological process you are considering, okay? So getting a small p-value is actually relatively easy by using a huge sample size. So I think it is very important that apart from the p-value, we have a notion of what is really important biologically. So if I have a significant p-value, it does not necessarily mean that what I observe has any biological meaning. So for this purpose, I think it is a kind of important to report also a kind of a confidence interval to see, or at least an estimate, okay, if what you really observe is really significant for you from your practical perspective. And another thing, what I think about p-value is a problem, but it depends on the model which you are using. So if you just use a simple t-test, you have some p-value, which might be completely not relevant because you might have some extra variability in your data. So maybe you need to use a mixed model, add some additional sources of variability. So if the p-value, if it is going to be meaningful, it is very important that you use a proper model and a proper test. And another problem with you have a p-value is like that this is, as Olga said, a random variable whose meaning very often people completely do not understand. And we have all this discussion between Bayesians, but people often consider p-values as conditional probability that the null hypothesis is true, which is completely not what it is, okay? So this is a concept which is often used, very often not properly interpreted by practitioners, which leads to many problems, okay? And maybe I just add a short comment. So I have heard a lot of criticism concerning p-values from practitioners. And we are often blamed for this, we statisticians, while the problem often lies somewhere different. So like, maybe I'll just give a voice to everybody else. So there is a problem of hacking for p-values. There are many, many other problems which are much deeper and which are not really directly related to the p-values themselves, but to the way the statistical research is conducted, okay? So thank you.
Thank you. Jaroslaw.
Good morning, good afternoon. My name is Jaroslaw Harezlak. I'm a professor at Indiana University. My training is in biostatistics, and I've been in the field now close to 20 years. And actually, it's funny how kind of people meet in different places. The first time I met Dr. Vitek was actually at the conference, when was it, 13 years ago, when I invited her for a session to talk about proteomics. And now she's still in proteomics. I left the area a long time ago. I concentrate mostly on kind of large data, but structured data. So I work in brain imaging, and for the past 5-6 years also in kind of the intensive longitudinal data, let's say, collected from wearable devices. Think about kind of Apple Watch on steroids, which is, I can actually get data at a sampling rate of 100 hertz, for example. I'm also a visiting professor at University of Wroclaw, and talking about history, Dr. Bogdan and I think we've known each other for 20+ years. And of course, Dr. Harrell, I've known your work for quite a while. Your book was very influential, especially in my early work on kind of as a data analysis person. I worked for a few years at the kind of at master's level. So thank you for writing a wonderful book.
Thanks.
P-values. I know already a lot has been said, and I won't really add much more, but just one comment coming from the brain imaging area. I would say, agreeing both with Dr. Vitek, Dr. Bogdan on the issue that usually there's this search for a parsimonious model, but the things are tested at the kind of in brain imaging as it's at a voxel level. So sometimes there could be hundreds of thousands, millions of voxels, and we try to find this region that's active due to some condition, due to some stimulus. Now, there has been, I think, before kind of, or maybe parallel to kind of genetics work and other kind of omics work, a lot of research in kind of correcting or finding the p-values that are correct in some sense have been done in brain imaging. And there are tons of packages. There is a lot of work where, in a sense, the proximity, the spatial proximity, the kind of the connectivity in the brain has to be taken into account. Otherwise, if we treat everything as independent, just those p-values truly don't make sense. Now, just to, on this, we're discussing the problems of the p-values and kind of reporting of the results and so on. Let me paraphrase the expression that we probably all know. I would say that all p-values are wrong, but some are useful. So let me finish with that.
That's a great thing to finish with, and I really appreciate all the comments of all three of you. And I'll just add some random thoughts, which is William Briggs has written a lot about p-values and how they never meant what Fisher even thought that they meant. That's the most shocking thing. And one of the things he's shown with a logical proof is that when Fisher said, either the null hypothesis is true or we have just witnessed an event of low probability, that the logical reconstruction of that statement is we have just witnessed an event of low probability. And the logic of the null hypothesis actually drops out of the logical construct. So you're left with, you've witnessed an event of low probability, and then what do you make of that? And so the p-values are indirect measures, and they're so indirect that they require multiplicity adjustment. That'll sound strange, but you only need a multiplicity adjustment because you need to consider what could have happened. And so p-values, when you have multiple looks at the data, a lot of things could have happened, and you have to be conservative to do a multiplicity adjustment about that. And Bayesian methods don't really know how to do multiplicity adjustments in the same situations because they're not using probabilities that are indirect. There's no way to do a multiplicity adjustment when you don't ask what could have happened, but you just ask what did happen. And so there's an exercise that I think everyone should do that sheds light on the issue, which is in the high dimensional situation, just formulate a prior distribution that you like and assume all the different genetic components or proteins are independent for now, or our knowledge about them is independent. And so you have 10,000 genes, and you get 10,000 posterior probabilities that the odds ratio is greater than 1.2. So you take something that's not null, you're looking for more than a trivial effect of a gene or a SNP, and you calculate 10,000 posterior probabilities, and you look at how many of those posterior probabilities are less than 0.02. And so you're pretty sure that gene is not important. how many are greater than 0.98, where you're pretty sure that the gene is important, and how many are between 0.02 and 0.98. These are the genes you should set aside and not comment on further, because these are ones for which we don't know whether they're important or not. The bad news is 85% of the genes will be in the 0.02 to 0.98 category. So for 85% of the genes, you don't know whether they're important or not. And the Bayesian posterior probability completely reveals what it is you don't know, because unlike the p-value, the p-value, 1 minus the p-value doesn't mean anything, whereas 1 minus the posterior probability means the probability something's not effective. And so unlike a p-value, the Bayesian method gives you a probability of similarity and not just the probability something's bigger than something else. So it really reveals the difficulty of the task, and that any cutoff in p-values is going to be futile, in the sense that you're going to have the majority of the features are going to be in the uncertain category, and you don't know what to do with it. So my personal view is that p-values, people know they have a lot of problems, and they have 3 times as many problems as people know about. So I think it may have been Olga that said the reason they're still popular is they're easy to compute. That's really it. And a lot of it is habit, inertia, and where did you go to school? So now we get into a lot of other questions, and I don't know, Michal, how much time do we have?
Sorry, Frank. Sorry, I got really carried with the talk, and I'm not really monitoring this. I'm deeply sorry, but I will let you know in a second. We have still 30 minutes.
How many?
30 minutes.
30 minutes, okay. So we have so many good things to cover. Type 1 and type 2 errors. I'll just mention that we're using the phrase type 1 error, but it's not an honest phrase. So we're using the phrase error, and there's no error involved. So all you're doing is calculating the trigger probability. What's the probability you're going to trigger an assertion? And that doesn't have anything to do with the probability of making an error. So probability of making an error is probability of being wrong. And so you're not calculating the probability of being wrong when you calculate type 1 alpha. So I'm trying to get people to call it type 1 assertion probability, because it's just the probability of an assertion. When you call it the probability of an error, you're elevating its value beyond what it's really worth. And we're finding investigators and FDA and a lot of other people are saying you're protecting yourself against making wrong decisions by controlling the type 1 probability. And that's not true. The type 1 probability has nothing to do with the probability of being wrong in asserting that something is there. So that is just it's in our graduate programs, it's in our textbooks, it's in our courses, type 1 error. We should have never allowed that phrase to be used because it makes our thinking strange. So most people know of the book 1984 by George Orwell. So one of the points in the book, which we're seeing in American politics right now, is if you start using misleading language, people start thinking wrong. And it gets you on a path of muddy thinking. So does anybody want to say anything else about type 1 and type 2 probabilities?
Yeah, maybe I can comment. So I also think that, when controlling type 1 error or elevation probability, right?
Just call it alpha.
Well, so I think it's probably not a good metric in the first place, because the best way to not have any false positives is to find nothing, right? And then for sure we have no false positives, right? But that's not why we're here. So at least in my field, what is important is how do we make decisions, right? And my applications may be different from some of the kind of classical biostatistics applications, in that we have 10,000 models, and we need essentially to say, okay, out of those models, what do we conclude, in a way that we can follow up on some of those proteins with better assays, maybe more precise assays, maybe larger sample size. So how can we narrow down a list of 10,000 proteins to a smaller list in which we will invest resources and time and do more work? And the way I like to talk to our collaborators is more in terms of, well, you can follow up on anything, right? So if you have an experiment with 3 replicates and 10,000 proteins, and you use the p-value cutoff and you use adjustment for multiple testing or not, you can follow up on any list that you want, but just make sure you understand the trade-offs, right? And you understand the consequences, because the worst thing that can happen is that you will just waste your time and resources following up on something which is not worth following. And so oftentimes, the way I say it is that my job is really managing expectations, because nobody prevents you from following up on everything, right? But just make sure you understand what the expectation would be of this type of decisions. And I think that's really an interplay, right, of how we make the decisions. So in terms of the overall objective and the utility, right, which includes cost, which includes our prior information. And also, well, it is true that sometimes these experiments work with very rare biological material, right? And they cannot have larger sample size, and they have like the flows cannot be easily addressed. So we just say, okay, let's just manage our expectations. And I think for us, it is easier because our results are not the last word in science, because people will follow up on these proteins with more data and more assays. But certainly the situation is different when you work, for example, with clinical data or clinical trials or something like that, where this is the model and you need to make the right decision and that's it, right?
So I think the idea of managing expectations, which I usually word as bringing bad news early, is really fantastic. And I just want to give you a friendly challenge on the first part of what you said. So think about 10,000 candidate features and you select 50 promising proteins. And so you have 9,950 losers. And so now you take the losers and you apply the best possible statistical method to them. It might be ridge regression. So you fit a high dimensional ridge regression logistic model with 9,950 features and get the predictive discrimination on the phenotypes or whatever your outcome variable is, and compare that predictive discrimination to the 50 winners. And I would bet money that the losers have more predictive signal in them than the winners. And doesn't that tell us to quit writing papers about winners?
Easily. Especially.
If I might jump in. Sorry, go ahead.
Yeah, go ahead, please.
If I may jump in here. So I think you touched on a very important topic here, Dr. Harrell, that it's kind of what's the goal of the analysis? Is it estimation? Is it prediction? And actually, there was a recent paper written by Brad Efron who said this estimation, prediction versus attribution. Yes, and here the last comment that you make, I think it touches on that point that what do we want from data as well? Do we want because we know that the two issues, get the best predictors and get the best predictive model. They cannot be really reconciled. So it's, I sometimes infuriate my colleagues because I give them very often a statistical answer. It depends. So you want this, you get one answer. You want something else, you get another answer. However, I have to say in practice, just the last thing is that whenever they say, no, we want the best classification, we want the best prediction. I say, okay, this is the algorithm. This is something that I would advise you to do. Immediate next question, immediate follow-up question is, and then we want to find what the important things are, meaning they are interested in estimation. So in a sense, they might say they're interested in something, but truly, I mean, at least in the field that I work, it's not like maybe like in marketing or in some business decisions where the importance is given to, at the end, to mechanical things. Can we understand what causes something? This is one of the next questions. And this is, I think, we're addressing problems of science, in other words.
So can maybe I add a point to it? So like, I think the very direct type of research when you look for features is when you do a drug development. Like what Olga is doing, she needs to point them some proteins which would be targeted by specific medicines. So we have to really rank them, and they are not going to test thousands of them. They need to have a relatively good ranking, so they can spend money and build very costly studies to really identify the drugs. So there are specific situations where really the feature selection is important, particularly, let's say, in the drug development. And now another question about and so I completely agree with when you have correlated features and when your purpose is the prediction, then, well, feature selection is not a good thing. But when your features are approximately independent, like it sometimes happens in genetic studies when we pick SNPs which are distant, then indeed you get better prediction properties if you identify certain percentage of most important features. So we have this bias variance trade-off. So when you basically try to estimate things which are close to zero, you are introducing into your prediction a bigger error than by neglecting or eliminating these features. So in the situation when your predictors are roughly independent, and you have such situations in some type of biological studies, actually going for a reasonable feature selection can improve also prediction properties. So thank you.
I think that's well said. And I just add to what all of you have said, another way to view part of the problem is I want a formal way to assess the hypothesis of parsimony. So I want to do something like develop the best prediction that does not assume parsimony, and develop the best prediction that assumes parsimony where you're doing feature selection, and then create a formal assessment of the null hypothesis that parsimony is correct. I want a formal analysis of that. And I think it will shed some light on this whole issue.
So maybe let me just give one comment. When I started to be a kind of a Bayesian, I did a beautiful basic course for students who later give their projects. And I had a student who compared two different species of trout. Basically, you could see from the box plot that the response was not different. But when you calculated the p-value, comparing means in a t-test, because of the huge sample sizes, the hypothesis was rejected, okay? So this is I wanted to add that very usually we have to accept that our hypotheses are, particularly the point hypothesis, that mu is 0 or not, but they are not, we are ever thinking about feature selection more in terms of ranking and really identifying features for which the signal is large enough that you can estimate it well compared to the variability of the estimation. Thank you.
And
So
maybe just, if I can add one more point, and this is really a way, I think, again, talking to biologists in my case, a way to bring Bayesian statistics more to the use of this field, right? Because if we say, okay, this is methodologically more rigorous and all of that, this is great, but it doesn't speak to them necessarily, right? But the way I think that what can make it work is to say that a lot of things we do in biology actually is based on a lot of prior information. Because when I look at my 10,000 proteins, in my data set, they're kind of all made equal. Maybe they have different variants, maybe missing values, but fundamentally they're all made equal. But it is not true in biology, right? When people design experiments, they have some very specific view in mind of what's happening in terms of the biomolecular function, what happens in terms of the technology, what can be measured easily, what cannot be measured easily. And so I think that talking about ways of using Bayesian inference to bring in informative priors, which are available either from previous experiments or from knowledge bases. I think that, at least in biology, this will be a very effective way of moving people away from the frequentist world to more of a Bayesian world. And I think in my research, this is really the path I see, which is probably the most straightforward for that.
I think that's well said. And now somebody has asked a question, can we remedy some of this problem with p-values by doing a holistic approach where you include, say, p-values and confidence intervals? And I'll just make a statement about confidence intervals for the panel to criticize. So confidence interval was invented about maybe 100 years ago, and we've had 100 years to come up with an interpretation of a confidence interval for a given data set, and no one has ever done it. And so why do we use an interval that has no known interpretation for your experiment?
I think it's for the same reason as the p-values, right? So it's easy to do, and it's in every paper. That's what we learn in Stat 101, right? So yeah, I think it's the same. Well, it's better than p-value. At least it shows you the magnitude of the effect, right? And in which direction and all of that. But fundamentally, it is the same.
You can think about confidence intervals as the limit of the Bayesian intervals when n goes to infinity. Okay, so Bayesian let's say prediction intervals often converge. The confidence intervals don't they? When you have when the sample size increases.
The main reason I try not to use an equivalence to Bayes is that the equivalence breaks down when you have a multiplicity adjustment, because that affects the confidence interval and does not affect the credible interval at all.
Which can be also misleading, I think, because I think like the Bayesian prediction intervals will also have the multiplicity problem. Like basically the multiplicity problem is like saying that when you do a lot of things, then large things can appear simply due to random fluctuations. And the same is true about small p-values, like about large posterior probability if you have multiplicity, if you have multiple comparisons. So this is very important to design the priors well enough that they kind of incorporate this problem. So I think if you do really spike and slab, so you don't use shrinkage priors, but you have a prior on the sparsity, I think it's important that it incorporates multiplicity. Again, in case of a shrinkage priors, I think also in the way you shrink, it is not entirely, in my opinion, true, but you get around multiplicity problem here as well.
Yeah, I think a way to say that is Bayes spends time getting the model right. It doesn't have multiplicity in the usual way, but it says, let's get the model right. Part of the model is the priors. And if you think that your population of effects is going to be sparse or small, then you want to select priors that do that. And that's part of your model. And how you interpret any one posterior probability is independent of other posterior probabilities you calculate. So there's no multiplicity in the sense of the frequentist approach. We do have some other questions, and I want to skip down to one about assessing normality and possibly transforming the data. And just to start the panel off, I'll make a statement that when we try different things, there was a paper by Faraway called The Cost of Data Analysis. It's the most frightening paper ever written in statistics, because he shows that the better statistician you are, the worse your confidence interval coverage at the end. So if you try different transformations, that has the most effect of anything at distorting your confidence intervals, making them too narrow. So the Bayesian would say, let's have a parameter for non-normality. So if you look at the Bayesian t-test, it does not assume normality, but it allows heavier tails. And you have a parameter for the degree of non-normality, and you have a parameter for the ratio of the variances. And so the Bayesian t-test doesn't make the normality assumption or the equivariance assumption, but it has priors that may favor those. But as the data set gets bigger, the priors wear off, and you'll go to something very non-normal or very unequal variances. So the issue of should we transform to get normality, I tend to answer no to that most of the time, but to select a method that doesn't depend on normality. And like Box and Cox would do that if you carried the lambda parameter forward in your confidence interval. Use a method that doesn't assume normality, that reflects what it is, how little you know, and it makes the confidence intervals wider if you don't know it was normally distributed. So that's the way I look at that one. Who has other comments about this question about my data is not normal, should I transform it?
I do, and maybe it's somewhat controversial, but again, coming like from the specifics of my field, right? Not necessarily applying to everybody. This is the thing I worry the least about in our analysis. And here's the reason. So again, coming up with the kind of our type of work, right? So what matters for us is to make the right decision, is to say which proteins do we want to follow up on and invest more money, right? And follow up with the different assets. So from my perspective, as long as we make the right decisions or close to right decisions, it's fine, right? So that's really the most important thing. Now, what can prevent us from making right decisions? Well, of course, like, our assumption of normality is important, but in my view, there are so many things that can go wrong in much bigger ways than normal distribution that this is really the biggest worry. And kind of from the statistical perspective, things that like violations of independence and batch effects, right? And some latent clusters. This will have a much bigger impact on our decision than, QQ plot, which is not exactly straight, right? But also, with my data scientist hat on, I'm actually very much worried about what happens before the data come to us, right? Because there is a whole life cycle of this data set, which happens from the moment when the data come out of the instrument and to the moment when it takes a form of an Excel spreadsheet, with nice columns and rows. And there are so many decisions made there in terms of what is kept, what is filtered out, what do we call a valid measurement, what is not a valid measurement. And these decisions are made in a very informal way, in a very kind of ad hoc way. And I think that these decisions, and sometimes people use cutoff, if my protein has more than 30% missing values, I remove it, right? Or if I have, some kind of interference, I remove it, right? And so on. Oh, oops, this run doesn't look good. Let me remove it, right? And so on. And those things, in my kind of experience, play a much more important role than what happens with the specific kind of normal distribution. And I think if we want to have the right procedure from the moment when the data generated to the moment where we make the decision, I think these are all the steps that we really need to worry about. And this means developing SOPs, developing protocols, and it also means making data available publicly and all the intermediate analysis steps for others to criticize. And at least in our field, this is not something we can do in R, unfortunately, because the original data are very large, like in complex and very specialized formats. So you have to have a pipeline of different tools. So what we've been working on in my group in collaboration with others, we have developed a repository for this type of workflows where we start with raw data. We have all the intermediate input-output files, scripts with different tools that people can store in a systematic way so that you can start your reproduction effort from the raw data or from some middle point or from the Excel spreadsheet. And then you can work with that. So long story short, I think there's so many other things to worry about. That normal distribution is important, but if we can still make the right decisions from that, I'm fine with that.
I can add to that, and this is, I agree pretty much with all the points that Dr. Vitek mentioned, but it's, I teach both in US and in Poland, mostly in US, and the thing is the emphasis given in Poland to the normality of the data, I would say it's bigger, at least from the student perspective. This is always when I always have a final project in my courses, and this is kind of the most important assumption that's being tested. One of the things with all the things about the bias sampling, the representativeness of the sample and so on that Dr. Vitek mentioned, this is all, this is all valid, and it's not only kind of in the biological fields, it's in other fields. These days, I would say, I don't want to give percentages, but my strong belief is that most of the analysis is done on the data not collected for scientific studies. Is the data that have been kind of gathered online, is the questions that we're asking from tweets, from Facebook posts, and so on, which are, normality. I agree, it's one of the least assumptions I would be worried about. Just the last comment that I will add here is that this is especially with applied researchers who think they know about statistics more than they actually do. They would say, oh, we'll just use a non-parametric test because it has low assumptions, where I have to stop them and say, no, that's not true. And the second thing they do, yes, for one variable, they use this non-parametric test, let's say Wilcoxon, Cross-Corvallis, whatever is kind of applicable. And then the next step will be they fit a model, let's say linear model, because they're interested in more covariates, they're interested in adjustments and so on. So in a sense, once they are worried about normality, and then they say, oh, okay, we're modeling already. We don't need this assumption.
Let me use that opportunity to put in a plug for semi-parametric models, because they really have the best of both worlds in the sense that they're transformation invariant. So they don't depend on your knowing how to transform the outcome variable, but they have the Wilcoxon test and a Kruskal-Wallis test as a special case. So that'd be proportional odds ordinal logistic model. So it's robust, it's super powerful. It allows you to get predictions, inference, handle all sorts of things, including longitudinal data with random effects. And so I think in my practice, I use semi-parametric models as a default. I almost never use a linear model anymore. So it makes the assumptions a parallelism assumption, but it doesn't make a single distribution assumption. And to not have anything like a normal distribution assumption for the residuals at all, but you just make an assumption for how the shape of the distribution of males relates to the shape of the distribution for females, is one level less assumption than the linear model.
So maybe I just, so I'm really not a practitioner, so I'm listening and learning from you. I will just tell you what I do and you can correct me. So like concerning transformation, I am not so much after normality, but for example, like making the data more symmetric. Like for example, when I try to fit a linear model and I see a leverage like long tails in my predictors, I try to normalize them by using some transformations to make them more uniformly distributed, because according to my experience, having outliers on the covariates really, let's say, deteriorates quality of a linear fit. So this is where I often use transformations, just to make the data more symmetric, not really trying to force them to be normal.
And you're really speaking about the independent variables.
Yes, independent, yes.
Yeah, I really agree, because they're more likely to be a little more linear the more symmetric they are. So the way I operationalize that is, if I don't transform the variable and I had a reasonable sample size, I will fit it with a spline function with 5 knots. If I take the cube root transformation, because that makes it more symmetric than the original distribution, I'll fit the cubic spline with 4 knots. So it allows me to have less nonlinearity by making it more symmetric, and it makes the numerical part of the model fitting better behaved. So I share that sentiment.
Thanks.
Doesn't make it linear, but it'll probably make it more linear.
Yeah.
Interesting.
Let's see what else is on our list. A lot of people are asking about causation, and I think we don't want to go down that very far, because that's just, that is an enormous topic. And I would just say that the number of cases where I've seen causal inference applied successfully to observational data is few and far between. And when you have the design that is a causal design, so you have experimental control with randomization, you don't need causal inference anyway. So I don't really trust causal inference unless the experimental design is a causal design in the first place. Where I do love causal inference is if you have randomization, but then you want to ask a separate question, which is, did people who actually took the drug do better than placebo? So we're dealing with a secondary question where randomization no longer applies fully. It starts off the treatment assignment, but then your treatment is not taken by the patient, and you want to do something like an instrumental variable analysis to say what would have happened if the patient did take the drug they were randomized to. That's a causal problem that's worth doing, where the randomization gives you the instrument and the instrumental variable as a good start. Or you can apply other methods of causal inference. But in general, I'm not seeing yet the compelling case for using the phrase causal inference when you have observational data.
Interesting. I would agree. So in molecular biology, it's a very similar situation, although I think that it has a lot of potential, because again, we have a lot of prior knowledge about the actual causal mechanisms at the molecular level. And so being able to express these known causal mechanisms in terms of DAGs, hopefully, right? And use this to kind of ask questions at the molecular level, I think in this particular case has the potential, because the DAGs can be well known, at least to a certain degree. The problem for us there is the data. We usually don't have the right data with a large sample size, which would support that. So at the end of the day, I have the same conclusion. It sounds exciting, but I have not seen successful examples like on the reasonable size, like real life problem.
Yeah. Does anybody else have a brief statement to make about causal inference? Something you can concentrate into a small...
2 sentences?
Yeah.
So one of the things that, so I agree with observational data, causal inference, there are rare examples of success, if there are really any, but one question that hasn't been addressed kind of here is heterogeneity. And this is something I think that comes to the front more and more these days, that this assumption that something is causal for a population, that's probably not true in general. That it might be causal for specific groups, specific, underlying mechanism or something, but making a causal statement in generality, that's probably will never be true.
I think Stephen Sen has written a lot about this, and he essentially says that you don't expect homogeneity of an effect, but you have to act as if everything is homogeneous, because the only way not to act that way is to do a 6-period crossover study so that you can make the right causal estimates on a per patient basis. And a single measurement is not going to allow you to do that, or even a parallel group randomized trial is not going to allow you to do that. So you don't have the luxury of estimating the heterogeneity with most data sets and most designs. So you have to act like it's homogeneous, even though you know it's not.
Interesting.
Did anybody else have a comment about causality? That's a loaded issue. There wasn't a follow-up question from the audience about transformations can get you into trouble because of interpretation problems. And I would just say that I don't think that's quite correct. I think there's so many tools that we have now for transforming the estimates back to the original scale that I'm not nearly as afraid of transformation as I used to be. Does anybody have any comment about that or anything else on our list of questions that people have asked, or any other topic?
Just a short one on the prior information. I know that kind of years ago, there was kind of a religious war between frequentists and Bayesians. Now it seemed it's more of people became more practical. And I don't know if I can call many researchers being practical Bayesians, but it's more, they use Bayesian methodology, not necessarily kind of from the philosophical perspective of Bayes, but it's just useful. And on that, the comments, especially Olga, that you made about including prior information, is informative priors. We don't have to go all the way Bayesian. We can just use regularization, introducing those more as penalty terms. So instead, for example, of ordinary ridge regression, we can use generalized ridge regression. So in a sense, this prior information can be introduced in the estimation procedure.
I just think it's hard to do inference at the end.
There's a beautiful thing of equivalence of penalized regression models and mixed models. So this is something at least I've been using in my work over the past decade, that again, it's not exact. The inference is not exact, but relying on the assumptions of kind of mixed modeling, we can actually have inference there.
Now, correct me if my understanding isn't right about this. I think of the penalized maximum likelihood estimation as empirical Bayes and not Bayes. And so empirical Bayes has a real disadvantage, which is, let's say you're doing meta-analysis using empirical Bayes and you have random effects for studies. Empirical Bayes doesn't recognize the uncertainty and the variance of the random effects. So it gives you uncertainty intervals that are too narrow all the way across the board. So it seems that that might also be the case for the approach that you mentioned versus a full Bayes approach.
Yes, so all the kind of sources of variability, yes, that's right, they are not taken into account. And it's even with random effects, sometimes we use them as if we estimated the random effects. Well, by definition, we cannot estimate them, we can predict them. And then the question becomes, are we doing inference on the predicted random effects given the true random effects, or we do this inference using unconditional distribution? And this is something I don't think it has been truly resolved in all cases. And it's still more of matter of an opinion than actual proof.
And you know, one thing that has been resolved is until you get to the complex question you just mentioned and wanting to do prediction or unconditional estimation, the original model development that you do with random effects in Bayes is trivial compared to what you have to do with the frequentist approach. It's way easier to handle random effects with Bayes. And you have more flexibility because you might have a non-normal random effects distribution or even a non-parametric random effects distribution. So Bayes, again, has some advantages.
So maybe I just add a comment. So I just participated in the panel for development treatment for rare diseases, where the sample sizes for clinical trials are very small. And I think this is a specific example which strongly calls for application of Bayesian statistics, because there is a prior knowledge. There is a huge prior knowledge from biologists, from medical doctors. So I think, I'm doing a lot of things which are actually trying to merge, like Jarek does, the frequentist and Bayesian methodology. I think there is a huge need in many fields for developing Bayesian approaches. And I think these rare diseases is a very important topic. But the problem is that if you come to the area of clinical trials, it is extremely important to set some standards on how the priors are developed, how the prior knowledge is really quantified. Because if we let it go in free, then there are going to be, let's say, I would say, huge problems in these types of formal applications of statistics.
Yeah, that's a perfect application of Bayes, and you really don't have many alternatives there in the rare disease situation.
Mm-hmm. Yeah. But I also think this is a kind of important, really, because you have not a large sample size, so the selection of priors is very important. The way you quantify the prior knowledge is important because it has an influence on the outcome. So I think some standards, like how to, let's say, quantify or the prior knowledge, I think developing some standard would be very useful here.
So I don't know when Michael is going to shut us down, but I wanted to leave how much, do we have any time left or we need to stop it now? So
Frank, so the next lecture, the next keynote lecture is actually a recorded video, and I couldn't muster enough strength to stop discussion. It's really interesting. It's really great to hear you all. So I think we could end in 5 minutes. How about that?
Okay, I'll leave thank you very much. And I'll leave the panel with a question to maybe end it with. So we have an exact non-parametric confidence interval for the population median, been around for a while. And there is no such thing as a non-parametric confidence interval for the mean. So it doesn't exist. So if you're really interested in being distribution free, should we use the mean less often and be using non-parametric confidence intervals for the median more often, even though it's a less efficient estimator? Let me leave that up for discussion.
Well, I agree. Yes, I agree. So we know that the mean is just extremely sensitive. So it depends, okay, if you really have very good data where you don't see outliers and so on, but mean is perfect, okay, because we have a law of large numbers and we have a central limit theorem. But whenever something bad happens, it's just going to deteriorate extremely. So I am actually, well, I think it a bit depends. It a bit depends, but you are definitely, I think, in a safer situation when you use a median.
I'm wondering if how dependent this is on experimental design. Because it's one thing that if you just have like a random sample of the population, and another if you have some hierarchical model with different layers of variation. And so what would that be?
And if you use semi-parametric models, you can estimate quantiles without the inefficiency of using sample quantiles. So it's still model-based, and it'll be more efficient than quantile regression.
Yeah, something to consider.
So I would agree from the theoretical point of view. Now, if I can convince my collaborators on that, that's a different story. And also with the thing that Olga mentioned about more complex models. This is something that it's so this is conference about R, WhyR, and we have now it's 15,000 packages. I even lost track of this number of packages. However, when I truly want to do something and I have a complicated design and I don't know the package, finding actually something for the median versus the mean, I think from the data analyst perspective, I think would be much harder. So it's not only computational issue, it's kind of developmental issue in terms of the methods for more complicated designs especially. But the second thing is, I would say, it really depends what we want to estimate. Like, sometimes I read literature, it's not really literature, just reports on mean income of households in US versus median income. Well, in that situation, mean income kind of loses its meaning because it's, yes, we get an estimate, but I'm not sure what this estimate is truly of. Median in such situation makes much more sense. Whereas where we have variables that we're estimating, if I have blood pressure, let's say systolic blood pressure, I don't care so much about is it mean, median, because probably I would get the same answer. We don't have these values that are truly multifold differences. So I agree with Gosha here. It's, I would say it depends, and depends on many levels.
And you reminded me of one of my the statistics that makes me most angry, which is Jeff Bezos, who heads Amazon. His income is $180,000 per minute.
That's about hours, yes? Isn't that similar to our income?
Per minute.
No.
So the mean would be much distorted if he were in your sample.
There are those calculators, and this is not with Jeff Bezos, but with soccer players. So somebody said, okay, put your income on the web, and that translates to how many minutes of, let's say, Cristiano Ronaldo's time that count for on the field. For some of us, it would be 2-3 minutes, of his playing time in a game.
Yeah. Oh yeah. Any final thoughts from any of the panel? Well, this has been a great discussion, and I really am glad to have been part of it. And I hope the audience enjoyed it. And they did ask some great questions. And I think to close it up, I think statistics is a field that's a science and an art. And I think you get a feel from that in this discussion. There's a lot of art to it, a little more than we maybe should have, but it's necessary. Much of it is necessary. And the practice of statistics involves a tremendous number of choices. And that's what I think gives us the most challenges, is how to make those choices. It also makes it fun. So thanks everybody for being part of this. And
thank you very much. Thank you for the kind invitation.
Thank you. And just because we are pretending that this is a real conference, I will announce 3 things. First and foremost, I want to thank all 4 panelists, but especially to Małgorzata Bogdan, who helped immensely in shaping the panel, inviting the guests. Thank you, Małgorzata. That was very kind of you. Secondly, Frank mentioned an article that actually was very soul-crushing for me. On the cost of data analysis by Julian Fairway. It was written by Julian very long time ago when he wasn't in Bath. I think he was in University of Michigan back then, or I think in States. And I allowed myself to plug this article in the chat. If you have a moment of your time, spare a minute or two and just read an abstract. It's really an amazing piece of work that I think is plugged too little. And the third thing, we are starting the next discussion panel, Performance in R, in 40 minutes, 6:30. And I will be very happy if you join us back then. So once again, to all panelists, thank you very much. And thank you for this great discussion. So we are not live. Thank you very much for being here.